Welcome back. I like to call this lesson the area of everything. Obviously, we're not going to cover everything, but after the lesson, you're going to find we're covering a lot of different shapes. So some of the shapes you already know the area for, like a triangle and a rectangle, but instead of just listing a list of all these formulas for areas for different shapes, what I want you to do is make connections between the areas of shapes you don't know and the area of shapes you already know. So here's where we're going. So after this lesson, you're going to understand that area is the amount of two-dimensional space taken up by a flat object. You'll also remember that units used are squared units because now we're measuring in two directions, two dimensions, so they're two-dimensional units, so it's units squared. Also, you'll be able to make connections and understand the relationships and patterns for calculating areas of different shapes. So we're going to start with a triangle, and then we'll move to some quadrilaterals, rectangles, parallelograms, kites, rhombuses, trapezoids. We'll also take a look at the area of a circle and relate that to, even though that's not even a polygon, we'll relate it to polygons. And then finally, we're going to head to a really cool shape, the regular hexagon. The regular hexagon has some really nice properties about it. And from deriving the area, the formula for area of a regular hexagon, we're going to generalize to all regular n-gons, all regular polygons. So here we go. So the area of a triangle, we're going to relate it to the area of a rectangle. And we all know that the area of a triangle is 1/2 base times height. And the key thing you have to remember with 1/2 base times height is that the base can be any of the three sides of the triangle. But what you have to be very careful about is that the height, whichever side you choose as the base, the height has to be perpendicular to the base. So to make things really easy, I'm going to start us off with a right triangle. And it's very clear that if we use this as the base, then instead of the hypotenuse, we're going to use this leg because this is the perpendicular side. So we're going to use the leg as the height, not the hypotenuse. So the formula we all know is 1/2 base times height. My question is, well, where does that 1/2 come from? So let's relate this triangle to another shape. So here is a congruent. I've basically just copied and pasted this triangle. So this is congruent. And if we simply just rotate this triangle and then translate it over, okay, it fits perfectly right there. And obviously, well, what shape do we have here? We have a rectangle. Okay, we have a rectangle. And what is the area of a rectangle? We all know that the rectangle has an area of base times height. So if this entire rectangle has an area of base times height, well, we can see that this triangle is just half of that rectangle. So it takes up 1/2 of base times height. So now let's move to the parallelogram. And we're going to simply relate the parallelogram also to a rectangle. So we're going to start with a rectangle, and we just recalled that the area of a rectangle is base times height. So now I laid the rectangle sideways this way. Okay, and then again, all I did was copy and pasted this, so I can guarantee you that these two rectangles, these turquoise rectangles, are congruent to each other. Okay, and so now what I've done is I've cut out part of this rectangle in a triangular shape, and you can kind of see the outline of it. And I'm simply going to translate this part that I cut out. I'm going to just slide it over here. Okay, and you're going to see that it's going to fit perfectly over here because this side of this triangle is what was originally the side of the rectangle. So now, what shape do we have here? We just have a parallelogram. So this parallelogram, the turquoise area that the parallelogram takes up, is still the same amount of area that the original rectangle took up. So what does that mean for area of a parallelogram? Well, that means that the area of a parallelogram is also just base times height, base times height. Yeah, but be careful because again, when we're talking about height of this shape, we're talking about the perpendicular height. So kind of this dimension here that goes straight up and down, that's perpendicular to this base. Okay. So area of a parallelogram is the same formula as area of a rectangle, base times height. So now let's go to the area of a kite and a rhombus, and these are really fun. So here I have a kite and a rhombus, and the first thing I want to do is add the two diagonals inside of both of these shapes. And to differentiate them, we'll call one of the diagonals D1 and one of the diagonals D2. And we'll say that the length of the first diagonal is D1, the length of the second diagonal is D2. So this D1 means this entire length of this kite, of this diagonal of the kite. D2 goes all the way across, okay, not just this part, but all the way across. Same thing for the rhombus. So the derivation and the formula actually ends up being the exact same. So I want to just focus in on one of these shapes. So let's go ahead and look at the kite more closely. So now we have, you have to also recall something about the properties of the diagonals of the kite and the rhombus. They intersect in perpendicular fashion. So this is a right angle right here. Okay, so what I'm going to do is let's examine this top half, okay, because this diagonal also bisects. It cuts the kite in half. So let's just look at this top half. Okay, so let's get rid of the bottom half. And then how long is this dimension? Instead of D2, because D2 went all the way across, this dimension is now 1/2 of D2. Okay, so D1 is this entire side down here, and this dimension is half of D2. Well, what shape is this? Well, obviously this is a triangle. Okay, and it's a triangle where the base of this triangle is this dimension here, D1, and the height of this triangle, notice it's perpendicular, so the perpendicular height of this triangle is 1/2 D2. So how do we get the area of a triangle? Well, the area of a triangle is just 1/2 the base times the height. Well, base is D1 and height is 1/2 D2. So let's go ahead and just substitute those values in. And then when you multiply 1/2 D1 times 1/2 D2, you simply get 1/4 D1 D2, D1 times D2. Okay, so that is the area of this triangle. But remember that the kite itself has two of these triangles. So for the area of the kite, we're simply going to double this 1/4 D1 D2. So when you double, okay, when you double 1/4 D1 D2, you just get 1/2 D1 D2. So that means the area of this entire kite, this entire green region, is 1/2 D1 times D2. And the exact same thing is true for the rhombus for the exact same reason. Okay, now let's go to a trapezoid. And where the kites and the rhombuses are really fun, the trapezoid is super fun. So here we go. So recall that a trapezoid is a shape, it's a quadrilateral that has exactly one pair of opposite sides are parallel. And those parallel sides are called bases. So to differentiate the bases, we're going to call this bottom base base 1. The top is base 2. Okay, and then that means that these opposite sides are not parallel to each other. Now be careful because a lot of you are looking at this and going, oh, that must be 90 degrees, that must be 90 degrees. It's not necessarily 90 degrees. Okay, it could be anything. It could be 88 degrees, could be 91 degrees. We don't know. So don't assume that that is a right angle. We don't know. But what we do know about this angle and this angle is if you look at two parallel lines cut by a transversal, these are CIAs. And we know that consecutive interior angles are simply going to be supplementary. So keep that in mind, that these two angles they're not right angles, but they're supplementary angles. So if this was like 89 degrees, this would be 91 degrees. Okay, that's very important. So now what I want to do is I want you guys, after you draw this shape and label it B1, B2, the length of this space is B1, the length of this space is B2. Now I want you to add to your diagram the midsegment. And if you don't remember what the midsegment is, that's okay. The midsegment is just the segment inside of this shape that connects the midpoints of the two legs. Okay, so it looks something like that. And the midsegment theorem for these trapezoids tells us that this length is actually the average of B1 and B2. Okay, but not important for right now. Okay, so there's our diagram. Now what I want us to do is this is going to take some visual imagination. I want you to imagine that this midpoint right here is a hinge, and we're going to flip this entire top part, okay, this top side, we're going to flip it around that hinge. We're going to rotate it around this hinge until it goes right around and slams down on the ground here. So we're going to rotate it in that clockwise direction. So what is it going to look like? Well, when you rotate this around this way, this is going to fit perfectly onto there. So it's going to slam down. So that's going to be airtight. Okay, and then what shape do we have in the bottom here? Let me make it a little bit more clear. What shape do we have? We have a parallelogram. Now, it's not a rectangle. It may look like a rectangle, but it's not a rectangle. It's a parallelogram. Okay, and how long is this dimension? It's B2. This is the top of, okay, this dimension is the top of this. I've just flipped it over. I've rotated it over. Okay, so this top part turns, it rotates, and boom, it slams on the ground and it rotates here. Well, what is this angle? This angle is that angle. I remember we said that this and this angle are supplementary because they're CIAs. Okay, so now when this is a parallelogram, we still know that these two angles are supplementary because they're no longer CIAs, but we remember that for a parallelogram, consecutive angles are supplementary. Okay, opposite angles are going to be congruent, but consecutive angles are supplementary. So if this is 89, that's 91 degrees. Okay, so we have a parallelogram. So what is the area that this parallelogram takes up? Well, we just learned that, okay? But one other dimension that we need to know before we get the area of the parallelogram is we need to know this height. How tall is this thing? What is this perpendicular height? Well, this height of the parallelogram is 1/2 the height of the original shape. So however tall this was, okay, this is half of that, okay, because remember, this is the mid segment, okay? So we have this dimension here, okay, and just to recall, the area of a parallelogram is just base times height. So how long is this base? This base is not B1, it's not B2, it's B1 plus B2. Okay, so the base, B1 plus B2, times the height, which is 1/2 the height of the original trapezoid. So the area of a trapezoid is just 1/2 of its height times the quantity B1 plus B2. And in the textbook, they express this a little bit differently. Okay, they take this and they simply do a little rearranging, and they express the formula for area of a trapezoid this way. B1 plus B2, that quantity all divided by 2 times H. Okay, so now let's go to the area of a circle. And to approach the area of a circle, I think we all know what it is. Okay, I'm not going to say what it is because we're going to derive it right now, but I want us to approach it by thinking like a student in calculus or pre-calculus. Okay, and I'll show you what I mean by that in just a second. So we start off with a circle, okay, and this circle has radius r. Okay, when I see a circle and when I talk about circles, I always think of my favorite food, pizza. And so one of the things about pizza is, well, do you like the crust of the pizza? I personally love the crust. I know a lot of people don't like the crust, but I like the crust. Well, what dimension is the crust of this pizza? What is that called? The length of going all the way around the circle, okay, or how much crust is there? Well, that is the circumference. And the circumference, as you recall, is 2 pi r. Well, 2 r's just gives you the diameter, so that's pi d, or d pi. Get it? D pi? Okay, so you have to recall what circumference is. Okay, so circumference, that dimension, is the crust, or it's the length of going, the one-dimensional length of going all the way around the outside of the circle. Another way to think of what circumference is if I took a circle and I snipped it at one point and I stretched out the crust, okay, and just made it a line segment, how long would that line segment be? It would be exactly 2 pi r, okay? Also, this d pi, this circumference equals d pi, that relates to, or circumference equals pi d, that relates to the definition of what pi actually is. It turns out that pi, this amazing irrational number, is the ratio of the circumference to the diameter of any circle. So if you look at any circle, no matter how big or how small, okay, the ratio of the circumference to its diameter, how long it is to go around the circle versus to go straight through the circle, that ratio is exactly pi for any circle. And that is really, really cool. Okay, enough of circumference. Let's move on to area. So what I want you to do is I want you to take this shape and I want you to cut it into many, many, many small shapes. Okay, so slice it into many, many, many congruent sections. And going back to the pizza story, okay, so we have this beautiful pizza. Think of your, maybe some extra large pizza, piping hot. It just came in from your favorite pizza place. Maybe it's, I don't know, Pizza My Heart or Pizza Hut, or maybe it's frozen pizza, maybe it's DiGiorno's, I don't know. But you now have to slice this pizza up because there's so many people, you and your friends are all going to share this pizza. So you have to slice it into many congruent sections. Okay, so that is going to look something like that. Now the circumference is still 2 pi r, but imagine that each one of these slices of pizza is exactly congruent. Okay, and now what we're going to do is we're going to rearrange these without changing the size or shape. Okay, we're going to rearrange each of these slices of pizza into something like that approximates a parallelogram. Now, is this exactly the area of a parallelogram? No, it's not. Well, why not? What's different? Because each one of these little crusts of these slices of pizza, these are curved. Okay, these are curved. So these are not exactly straight. It's not flat. It's not straight. So it's not going to be exactly the same as a parallelogram, but it's going to be very close. Now, what happens if you slice this into many, many more, if you make these slices super small, okay, and make many more of them? Okay, then what happens to the area? Well, the area approximates a parallelogram really, really closely because as these get smaller, okay, they become less round. It's almost like they become almost flatter in a sense. Okay, and if you were to able somehow magically to cut it into infinitely many slices, okay, then that's one of the ideas of pre-calculus called limits, where as the number of slices approaches infinity, that area will equal the area of the parallelogram. Another big idea that you're going to learn in calculus is integrals. And basically that is learning how to calculate the area underneath a curve. Okay, and to calculate the area under a curve, what you're going to do is you're going to actually use this kind of thinking. Instead of calculating the area under the curve, you're going to take that area under the curve and slice it into many, 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 many pieces like this that are, instead of approximating triangles, they're going to approximate rectangles. Okay, and as you have more and more of those rectangles, you're going to get a very accurate result for the area under a curve. Okay, so what is the height of this parallelogram? Well, the height is actually just r. Okay, it's the radius of the circle. So the big question is, how long is this base? Well, this is the crust of the pizza, but it's not all of the crust. If you look at this, this has crust up here. So that's half of the crust, and that's half of the crust, or half of C, half of the circumference. So the base length is just half of the circumference. So half of the circumference, instead of 2 pi r, it's just going to be pi r. So what is the area of a parallelogram? It's just the base times the height. So it's pi r times r, which is just pi r squared. So now let's look at the area of a regular hexagon. To examine the area of a regular hexagon, we're going to go back to one of the most basic shapes, one of our favorite shapes, and that is the triangle. So before we get to the area, we have to go through some new terminology first. Okay, so if you have a regular hexagon, it looks something like this. So go ahead and draw your regular hexagon. Just sketch it to the best of your ability. Okay, and I want you to look at the center of this hexagon. If this was a circle, if there was a circle circumscribing this, the center of the circle would be the center of this hexagon. Okay, so that is one of the key terms we're going to learn. But let's go over all the key terms. Go ahead and draw the diagonals. And the center of this regular polygon, the center of any regular polygon, is the same as the center of the circle that would circumscribe the polygon. It's exactly what you think it is. It's this point that's right in the center. A radius of a regular polygon is the line segment that goes from the center to a vertex. Okay, to a vertex, not to the side, but to the vertex. Okay, remember, these corners are called the vertex, the vertices, and these flat parts are called the sides. So side, 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 vertex, vertex, radius, radius, radius. So how many radii do you see here? 6 radii. Good. Side length, so this is a side, and its dimension is little s, or side length. Now the apothem is brand new. So the apothem is when you go from the center and draw a line segment straight down perpendicular to one of the sides. Okay, that's the apothem. And that is not going to be as long as the radius. You can see that the radius is going to be longer. Let me draw the apothem for you in just a moment. A central angle. A central angle is simply one of these angles, okay, right here. So if you were to start at this point and go all the way around to this point again, that would be 360 degrees. But if you stop right here at the central angle, how many degrees is this central angle going to be? Well, all 6 of these angles are congruent to each other, so this is just going to be 1/6 of going all the way around, or 360 divided by 6. So this central angle is going to measure 60 degrees. This is going to be 60 degrees right here. Okay, that is called a central angle. It's an angle formed by 2 consecutive radii. Okay, and so it's right there. The central triangle is this triangle right here. This triangle right here. It's formed by 2 radii. Okay, so it has a central angle at this vertex. Okay, and how many central triangles do you see in this diagram? You see 1, 2, 3, 4, 5, 6. 6 congruent triangles. Those are all central triangles. Okay, and there is the apothem. The apothem, again, is the line segment that goes from the center directly to the side. And when I say directly, I mean in perpendicular fashion. Okay, and take a moment to examine this diagram and convince yourself that this is not going to be as long as a radius. It's going to be shorter. Okay. So now, to figure out the area of a regular hexagon, let's rearrange these 6 triangles. So there's 3 of them, and there's 3 more. And notice that they're going to fit perfectly into each other, just like this. And by the way, we said that for a regular hexagon, this is 60 degrees. And can you figure out how much this angle is and this angle is? Well, it's probably intuitively, you're probably guessing that this is a 60, 60, 60, and it is. Okay, how do you know that? Because we know that this entire angle would be n minus 2 times 180 divided by n, right? N minus 2 times 180 is the total of all the interior angles, the measures of the interior angles, and then we divide it by n because each one of them is congruent. And there's 6 of these, there's n of these, so you just divide it by n. So this is 120 degrees, and this radius bisects that 120 degrees. So this central triangle is indeed equilateral and equiangular. It's 60, 60, 60. So that means that the side length is the same as a radius. Okay, so these are all 6 equilateral triangles. And when you rearrange them, they're going to fit inside of each other perfectly like this. And what shape do we have here? We have the parallelogram. And the parallelogram has an area of just base times height. So how long is this base and how tall is the height? The base is just going to be half the perimeter. Because if you look at the perimeter, it has 6 of these sides. Well, this just has 3 sides and this has 3 sides. So it is half of the perimeter. Okay, now how tall is this? What is the height? So if you go from here to there, what was that new term we called? It's like going from here to here. That is the apothem. So what does that mean? That means that the area of a regular hexagon is 1/2 the apothem times the perimeter, or technically 1/2 the perimeter times the apothem, but you're going to see the formula in the textbook represented this way, 1/2 apothem times perimeter. And it turns out that the area of any regular polygon, even if it's not a hexagon, is also 1/2 the apothem times the perimeter. So I want to generalize and look at a regular n-gon, okay? And I know we already know the formula. It's 1/2 apothem times perimeter, but let's take a look at that. So now instead of a regular hexagon, go ahead and draw this shape. What is this shape? 1, 2, 3, 4, 5. It's a regular pentagon. Okay, we know that the formula is 1/2 apothem times perimeter, but let's go ahead and use this formula and show you a little bit more specifically how this relates, how the apothem and the perimeter relates to this regular pentagon. So by the way, how do you get perimeter? It's just n, which is the number of sides, times s, which is the side length, right? It's just, so in this case, it's 5 times s. However long the side length is, there's 5 of them, so it's just 5 times s. Now to find the apothem, we need to examine a central triangle. So here is a central triangle. Go ahead and draw a central triangle. Remember that this vertex is the center. It's the center of the regular polygon, and then you just draw 2 radii. So this is a central triangle. So the question of interest is, well, how big is this vertex? It's not going to be 60 degrees. Well, how are we going to figure that? If you start from here and go all the way around, that's 360 degrees, but instead of going all the way around, we're only going 1/5 of the way around. So that central triangle, or central angle, is only going to be 1/5 of 360. By the way, here is the apothem. So I went ahead and enlarged this central triangle. This gray triangle is just the same as this. I enlarged it, and then I dropped the apothem. Remember, the apothem is perpendicular to the side. So this is just the side of the regular pentagon. Okay, this is a radius, this is a radius, this is the apothem. And here we have it. The central angle is 72 degrees, just 360 divided by 5. Okay, now this angle is not going to be 72 degrees. This is half of that central angle. So it's going to be 36 degrees. This dimension down here, this entire side is the side length. So this is half of the side length. So if you look at this triangle right here, what do we have? We have a right triangle where we know the dimensions of the 2 legs. We know that one of the legs is A, one of the legs is 1/2 of the side length of the entire pentagon, and we know one of the acute angles measures 36 degrees. So how are we going to find how long A is? Well, we're simply going to use some trigonometry, some right triangle trig. So from the perspective of this angle, 36 degrees, this is the opposite side and this is the adjacent side. So we know SOHCAHTOA, TOA, tangent is just opposite over adjacent. So the tangent of this angle measure, the tangent of 36 degrees, is equal to 1/2 the side length, that's opposite, over apothem, which is adjacent. So rearranging to solve for apothem, the apothem is just going to be this dimension, which is 1/2 the side length of the entire pentagon, divided by tangent 36 degrees. Okay, so let's summarize everything that we have learned. Okay, sorry. So triangle, 1/2 base times height, rectangle, base times height, parallelogram, same as rectangle, kite and a rhombus, 1/2 d1, d2, trapezoid, 1/2 height times the quantity b1 plus b2, circle is just pi r squared, and then any regular polygon is 1/2 apothem times perimeter. Remember that perimeter is n times s. All right, guys, that's all I have for you. Hope you enjoyed the video. Hope you made really good notes. Enjoy the homework. It's L53 is the area worksheet. L54, you have some problems here on page 614. See you in the next video.